Welcome to this explainer. Today, we're diving into a truly profound industrial transformation. We're looking at a company that started back in 1993 as a simple graphics startup and systematically evolved into the foundational architect of global computing infrastructure. We are, of course, talking about NVIDIA. And we're going to trace exactly how their hardware and software became the undisputed engine of the artificial intelligence revolution. We'll be doing this strictly by following the established data and the underlying engineering principles. Here is our roadmap for today. We'll start with the birth of the modern GPU, then look at CUDA as the software foundation, and explore how the AI revolution actually began. After that, we'll cover Blackwell and Datacenters, touch on Vera Rubin and Agentic AI, and finally, wrap up with a new industrial infrastructure. Let's jump right into Section 1, the birth of the modern GPU, from a Denny's booth to parallel computing. So, looking back at those three engineers sitting in a Denny's booth in 1993, what in the world is the actual difference between a standard computer chip and their invention at the GPU? Well, let's break this complex engineering down into a simple, everyday metaphor that anyone can picture. Imagine a busy restaurant kitchen. A traditional CPU, or central processing unit, is like having one incredibly fast, highly skilled master chef. This chef is brilliant at cooking one really complex meal at a time, moving sequentially from step to step. Okay, that makes sense, but what about the GPU? Right, a GPU, or graphics processing unit, is built completely differently. Instead of one master chef, a GPU is like having 10,000 line cooks in that same kitchen. They might not be able to cook the entire complex meal all by themselves, but they can chop 10,000 carrots at the exact same fraction of a second. Wow, so they're all working simultaneously? Exactly. This is called parallel computing. It was originally designed to calculate thousands of pixels on a screen all at once. But as we'll see, it turns out this is also the exact mathematical structure required to build artificial intelligence. Moving right along to Section 2. CUDA, the software foundation building the moat. Wait, so if the hardware is just about parallel computing, why couldn't any other company just build their own army of 10,000 line cooks and take over the market?
That is a great question. The reality is hardware is practically useless without instructions. So back in 2006, NVIDIA launched the CUDA software platform. If the GPU is that massive factory of 10,000 workers, CUDA is the foundational electrical wiring and the master instruction manual. It tells those workers exactly how to work together on tasks other than just graphics.
So they invited the world to build on their platform.
Precisely. By opening up their chips to general-purpose computing, NVIDIA created a massive ecosystem. Today, there are over 5 million developers and more than 3,000 accelerated applications built entirely on CUDA. It locked in a massive competitive advantage, creating established switching costs. Meaning if a company wants to leave NVIDIA, they don't just buy new hardware. They have to tear out all that foundational wiring and rewrite decades of proven optimized code.
Now for Section 3. The AI revolution begins, the tipping point of 2012. So NVIDIA had built the parallel hardware and the software manual to use it. But how did video game hardware suddenly become the engine for global artificial intelligence? Well, everything came together in 2012 with a breakthrough known as AlexNet. Researchers at the University of Toronto were trying to train a neural network to recognize images. They realized something crucial. The massive matrix multiplication required for AI was identical to the math used to render graphics. So they literally just used gaming chips? Yes. By using just 2 NVIDIA gaming GPUs, they proved they could train their AI model dramatically faster than using traditional CPUs. The entire academic and business world took notice immediately. The framework was proven, so NVIDIA didn't even have to pivot. Not at all. The world's computational needs simply shifted to exactly what NVIDIA had been methodically building for 20 years. That brings us to Section 4, Blackwell and Datacenters, the infrastructure era. Now, you might be wondering, why can't we just keep making single computer chips bigger and bigger forever to get more power? It seems logical, right? But the answer is a hard physical boundary called the reticle limit. In semiconductor manufacturing, the machines that print the microscopic circuits onto silicon can only expose an area of about 800 square millimeters at a time. You physically cannot print a single solid chip larger than that, so it's an actual physical limit of the printer. To break past this established boundary, NVIDIA had to engineer a completely new approach. So if you can't mold one massive block because your machine is too small, what in the world do? You use chiplet architecture. Think of it just like classic Lego blocks. You manufacture two smaller, perfectly engineered blocks and snap them together seamlessly. Oh, that's a brilliant way around the problem. NVIDIA created two massive silicon dies and linked them with a staggering 10 terabytes per second connection. Because that connection is so fast, the software sees them as one single unified processor. This snap-together chip contains an incredible 208 billion transistors. It's a triumph of physical engineering over manufacturing constraints, culminating in the Blackwell architecture released in 2024. And the market has responded to this physical infrastructure with undeniable financial force. Just look at this number. NVIDIA reported an annual data center revenue of $194 billion for fiscal year 2026. That is just a staggering figure. It is, and it's not speculative. It's established economic reality. This business has scaled nearly 13 times since the emergence of ChatGPT in late 2022. The demand for computing power directly translates to revenue for companies deploying AI, which is driving a massive capital expenditure cycle. Which brings us to their market share. NVIDIA currently commands approximately an 80% market share in AI accelerators. 80%? That's incredible. Through an objective lens, this dominance is the direct result of their 15-year head start with the CUDA software platform, combined with their relentless yearly cadence of hardware innovation. They provide the complete, proven framework that enterprise customers and sovereign nations trust for their critical infrastructure. Let's look ahead in Section 5, Vera Rubin and Agentic AI, the future horizon. So, what happens after standard text generation models? What exactly is Agentic AI? To understand Agentic AI, let's use a simple real-world example. Think of basic text generation, like the early versions of ChatGPT, as a child reading a recipe to you from a cookbook. It's helpful, for sure, but you still have to do all the actual work.
Right, you still have to bake the cake.
Agentic AI is like that same child autonomously walking into the kitchen, fetching the flour, the eggs, and the sugar, and baking the cake themselves. Agentic AI systems don't just generate text. They reason through multi-step problems, access your files, use software tools, and take autonomous action to complete complex tasks. But baking that cake requires retrieving ingredients incredibly fast, right? It sure does. Agentic AI requires systems to constantly fetch data from memory, and that is why the upcoming Vera Rubin platform is fundamentally different. Slated for the second half of 2026, it delivers 8 exaflops of compute. Exaflops? That sounds intense. What's the key difference? Crucially, it integrates technology from a company called Grok, providing 55 times the memory bandwidth of previous generations. This extreme memory speed is the physical requirement to allow these autonomous AI agents to access tools and files without bottlenecks. Which brings us to our final section, Section 6. The new industrial infrastructure, a multi-trillion-dollar reality. When we step back and look at the sheer size of this shift, the objective projections are astounding. Over the next 5 years, the global transition to AI infrastructure represents a $3 to $4 trillion opportunity. A trillion with a T. That's a massive scale. It is. And this isn't just about software anymore. This is about physical construction, energy grids, cooling systems, and networking. Every major enterprise and sovereign nation is treating AI compute exactly like electricity or internet connectivity. It is foundational, required infrastructure for future economic productivity. As NVIDIA's CEO, Jensen Huang, noted, we are kicking off the greatest infrastructure build-out in history. Think about the sheer physical scale and historical magnitude of what we've covered today in this explainer. From a diner booth in 1993, to solving the math of pixels, to engineering silicon chips that defy physical limits, all the way to laying the concrete and steel for global AI factories. The foundational principles of computing have completely shifted. As this trillion-dollar infrastructure becomes as ubiquitous as the electricity powering your home, we leave you with this question. How will your industry adapt to the era of accelerated autonomous intelligence?